Hey, good morning, everyone. I hope you had a wonderful night and you met somebody new last night. So a couple of things for today. So today we are going to really just do much more of what we did yesterday. So we are now on Theme 2, Breakout Session 2. So you know what to do. You are going to go to your breakout assignment and you are going to work on those research questions that we have for it. And then we are going to do a cross-fertilization event again from 10 to 11. So you will come back here. And then this evening, at 11, we will go and do Theme 3, Session 1. Okay, so you know what you're doing. So a couple of suggestions. I think everybody's doing an amazing work. And at least in the groups that it was just wonderful to see the ideas flying and people brainstorming. So I think everybody's doing a fantastic job. Some posters don't have the theme and the topic on the top, so it will be hard for us to put this together. So please remember to put your theme and your topic on the top of the poster. And also, it will be wonderful if everybody made an effort to turn whatever you're discussing into a research question, because that's what we are trying to do in these 2 days. So yeah, so maybe one of you can take the lead and say, hey, can we convert that into a research question? So we can do that. And other than that, anything else? Oh, the last thing. Yeah, I think we are here to build a community. So at least me, I propose to myself to meet everybody in this room, to talk to everybody in this room. I don't know, probably you won't do that, but just really make sure you meet a lot of the wonderful people that are here. So don't be afraid to go to anybody and talk to them, even if you don't know them. So if you see me coming to you, you know what's happening. Anyway, so yeah, go to your breakout room. And anything else? No? Okay.
Move on to Theme 3 now, which is about assessing the capacity of microbes to adjust to global change and modify environmental conditions so that we can improve predictions of how global change is going to affect biogeochemical cycles and ecosystem function. So as previously, we're going to kick this off with 2 short presentations to highlight some of the science innovation areas. So first up is Scott McCain from MIT, who's going to talk about microbial rate estimation using proteins and proteomes.
Okay, so thank you to the organizers for this opportunity. I've loved talking to people so far, and it's a really wonderful group of people, and I'm really excited to talk to you about this work that we've been doing on estimating rates using proteins and proteomes. So of course, many of us want to go into the ocean and get a bunch of water and then filter that water and extract perhaps DNA, RNA, or protein, and then try and use various technologies to sort of reconstruct the sets of rates or the sets of processes that are happening back in that water. What are the rates of nitrogen fixation, the rates of exchange of vitamins between these spheres or the idealized microbes, and how do we, I think one sort of general question is, how do we translate these really high-dimensional and complex data sources like metagenomes, metatranscriptomes, and metaproteomes into some sort of quantitative rate estimate? Or how do we translate that big data source into something that we can say about a time-dependent process that's actually happening in the water column as we're filtering it, or after we've filtered it, I guess. So for example, we might be focused on proteins, and we might be interested in nitrogen fixation. So if we then look at the protein nitrogenase, and its cognate rate is, of course, fixing nitrogen, we might go into the ocean and then compare the amounts of nitrogenase in one part of the ocean and then the amounts of nitrogenase in another part of the ocean and say, well, on this right side, there's a lot more nitrogenase. So maybe we can then say there's more nitrogen fixation, which seems like a reasonable kind of statement to make. But even in making that statement, there's a whole variety of assumptions we have to make about the kinetics of nitrogenase and the amount of activity per nitrogenase. And this is true for every protein and every enzyme that's converting one product into another product or transporting something from outside the cell to inside the cell. And so just from a sort of a very basic way of framing this problem is, are protein abundances correlated with their actual rates that they're mediating? And when I started off in this project, I sort of had this naive assumption that, of course, they must be correlated. There's lots of reasons that you can come up with for sort of making that assumption. But what we found is that empirically, I haven't actually seen this assumption really rigorously assessed over many different types of rates and many different proteins. And so what we needed was to look at, ideally, many different protein levels. So we want to see a big dynamic range in the amount of different proteins across different conditions, and then also their corresponding in vivo reaction rates. So for example, we might be interested in nitrogenase, and then we'd want to pair variation in the amount of nitrogenase to variation in the amount of nitrogen fixation. And also, we do this across different proteins, so you get a sense for what should we expect when we're trying to make these sort of rate estimates in the wild. And then, of course, with different rates. And even more ideally, because we're thinking big, we want to do this across different taxa as well. So what we ended up doing was aggregating a large data set, mostly leveraging data from the model organism literature, specifically using Baker's yeast and E. coli. And in these different data sets, we have paired reaction rates with proteomes across a wide variety of different conditions. So for yeast, there's 15 different conditions, experimental conditions. And in each of these conditions, we have a whole proteome and then a bunch of different intracellular rate estimates, things like steps of glycolysis or rates of ammonium uptake. And then for E. coli, there's 25 different conditions. So these are really big data sets in terms of diversity of environmental exposures. And these data sets are also all in steady state and in pure culture. So we're really just trying to say, even under these idealized conditions, how well do we get, how correlated are rates with their cognate, or correlated are proteins with their cognate rates? And so to look at that relationship, first we want to sort of transform out the differences in that relationship you might expect just from enzyme kinetics. So we use the Z-score transformation to transform both the protein abundances and their corresponding rates. And then we also use a Bayesian hierarchical model to look at this, to quantify the linear relationship between proteins and their corresponding rates across these two different taxa. So you can think of this like a correlation coefficient. And just to kind of give you an example of what some of these data look like, if we're focusing in on ammonia transport, so we're going from outside the cell to inside the cell, we can see the ammonia transport rate, the transformed ammonia transport rate on the y-axis, and the ammonia transport abundance on the x-axis. And you can see that the relationship is completely uncorrelated. There's no clear relationship between, at least in yeast, under these conditions, the rate of transport and the amount of the protein. And so, but ideally, we do this across many different proteins and many different taxa as well. And so here, the correlation coefficient is about 0. But now what I'm showing you is the correlation coefficients across a bunch of different rates. Each of these ticks on the y-axis are rates to enzyme abundance pairs. So in the previous slide, I showed you an estimate that's about we okay?
Carry on.
And this is why I switched to modeling. The correlation coefficient is around here in the previous, correlation coefficient is around 0. Okay, perfect. Should I use this stick? Is that okay? So we're around 0. You can see my trembling hand as well. So around 0, but of course, what we found is actually there's a huge diversity in this relationship. And so what this means is that for some protein rate pairs, when the protein goes up, are people still online? Or? Yeah. I'm so sorry. Okay, so you can see that some of the correlation coefficients are high and some are low. So that means actually for a lot of proteins, the reaction rate can be totally independent of the amount of the protein. Sometimes it's highly correlated, but other times you can see an increase in the amount of the protein and the reaction rate actually goes down. And this was super surprising to me. So I was saying that in the previous slide, the correlation coefficient was about 0. And so that meant that the rate is almost totally independent or linearly independent of the corresponding transporter. And what was surprising to us is that there's a huge diversity in both the yeast on the left and the E. coli data set on the right of these relationships. And so just to clarify again, the x-axis is this Bayesian correlation coefficient, just sort of like a Pearson correlation coefficient, and the error bars are the confidence interval around that estimate. And so this was really surprising to me personally, just in terms of interpretation. When I see a protein goes up, then I sort of had an implicit assumption that the corresponding process that the protein was mediating also went up. And I think that this is showing that it's actually really hard to know if that's actually happening in vivo. And we've spent a lot of time trying to figure out why some proteins are up here and some proteins are up here. And the short story is we really don't know. And if you have any ideas, then I'd love to hear them. So I think this is suggesting that making quantitative rate estimates of microbial communities will be really challenging with single proteins. But of course, if we have some mechanistic constraints, so for example, if we knew that the protein was substrate saturated for some reason, then we might be able to get away with using single proteins. Or if we had paired environmental data, this is completely ignorant of the environmental context. So if we knew something about the environment, then maybe we can really constrain these rate estimates better. And that's obviously a big plug for Biogen Escapes. But what we thought is, can we use the rest of the proteome? Can we bypass these two different requirements of either having mechanistic constraints or paired environmental data? Can we use the rest of the proteome in context to try and estimate these intracellular rates? And so going back to this ammonia transporter example here, you're seeing the single relationship between ammonia transport and the ammonia transporter abundance and the transport rate. And this has a correlation coefficient of about 0. But what I'm showing you just sort of is considering this additional protein context. Of course, ammonia, once it gets into the cell, is used by other proteins. It's transformed into something else. Or maybe the transporter itself is modified in some way. Maybe the kinetics are altered. And what if we use that additional proteomic context to try and estimate that individual rate? And so what we did is use a very simple statistical technique called lasso regression, where we considered a model of all the rest of the proteins in the cell to estimate an individual rate. So in the previous slide, in the previous part of the talk, I was really showing you how the single rate corresponds to the abundance of this transporter, and I was showing you the beta-1 coefficient, or that's that Pearson correlation coefficient. But if we consider the rest of the proteins, so you actually put the entire proteome into the model to estimate ammonia transport rate, what we find is that at least in yeast, the ammonia uptake rate is highly predictable. So you can see the observed rate on the x-axis and the predicted rate on the y-axis. And here, this line is the one-to-one relationship, and the R-squared of this model is around 0.8. So that's really exciting from a rate estimation perspective if we use this additional context. But what you might be thinking is, did I just cherry pick this individual rate from a whole distribution of rates, and is this the best one, or is this kind of representative of most rates that we can estimate within cells? And actually what we found is that many different rates are highly predictable. So here I'm showing you the cross-validated R-squared from 233 different intracellular rates across various different conditions. And this is specifically in the yeast data set. And you can see that most of the rates are actually around an R-squared of 0.8, suggesting that rates are highly predictable, at least in these idealized conditions. And so I'd just like to finish. I don't really know how much time, 1 minute? Okay. I'd just like to finish by saying that I think that Biogen Escapes can learn a lot from different fields that have used various techniques, especially rate estimation is sort of also prevalent in the cancer prognosis field, where single proteins have historically been used to estimate the rates of tumor growth in actual patients. And these prognostic markers were significantly improved by adding in the additional sort of proteomic or transcriptomic landscape. And I think that I'm really excited about how these different data sources can help with rate estimates. So I've shown you that there's this highly predictable or highly variable protein abundance to rate relationship, but that we might be able to estimate rates using whole proteomes. And then for biogeoscapes, I think that I'm really excited about this in terms of being able to actually estimate rates in complex assemblages. I think we need to be considerate of the time scale that we pair environmental data with the proteomes, because there's, of course, this whole proteomic context, which is a reflection of that time scale. And then I think we need to be clear about what we're going to use the rates for to assess our predictions. And that's it. Thank you.
Okay, thank you, Scott, for dealing with that. There's a question online. Alex,
Four questions here.
Question. So maybe can we go online first?
Yes.
Oh, yeah, go ahead, Adam, and unmute.
All right. Can you hear me?
Yeah.
Okay, so my question is about the low correlation. Isn't it that a reaction rate is equal, like some kind of a reaction coefficient times the substrate concentration, and where the reaction coefficient is proportional to the enzyme concentration, but also to the substrate concentration. So the fact that you have a low correlation is just due to the fact that you have variation in the substrate concentration. Isn't that the missing ingredient?
I totally agree with that. I think that the problem is that we don't know under which conditions the substrate is going down or up. And then there's also the third issue of allosteric interactions with individual proteins. So I totally agree with you that variation in the substrate is probably contributing to this variable relationship.
Hi.
Oh. Alex, look, let's try and make the questions and answers quick, and then everyone can get to ask their questions.
Hi, Alex Warden. That was really cool. I was just wondering, so I don't know the methods used in the yeast papers or whichever one, E. coli, yeah. But, you know, proteomics has this often trouble with the less abundant proteins, and perhaps when you're working in a single organism, you get more of the dynamic range of all the different proteins, which would be very hard often in a metaproteomic space. And I'm wondering, do you have a sense of, does it matter that you get sort of the low and high abundance proteins to get these relationships you're seeing, or can you be working in the top end of the spectrum and still get this kind of normalization or positive benefit of having the whole proteome?
So one thing I didn't talk about was how many proteins we need to make that estimate. And you actually only need a few, so like 10 to 20 different proteins.
Can they all be highly abundant?
Yeah, and I haven't found any relationship between the like whether or not they're included as being, yes, I think you can use the highly abundant ones, I guess what I'm saying.
Yep. Hi, it's Scott Gifford, UNC Chapel Hill. So great talk, Scott. And my question was, when you did the yeast and the E. coli, and you had those trends, but then were there any overlaps between the ones that had the high correlations in the organisms, but across the yeast and the E. coli?
We mapped the homologous proteins and saw no relationship. So if it's like a protein that behaves in one way in yeast is behaving totally differently in E. coli, which is I don't know why. I was hoping that they would have. Yeah.
Hey, I think we're going to have to stop. Sorry, Julie. Julie Granger there, so you can go into the chat.
Thank you for giving the opportunity to talk today. I'd like to talk about ocean ion cycle. The left side figure shows how phytoplankton uptakes nutrients from seawater. In addition to macronutrients like phosphorus and nitrogen, some trace metals are required for phytoplankton growth. For example, iron and zinc. These trace metals are used for active site or cofactors for enzymes to facilitate metabolism. And iron is used for nitrogen fixing nitrogenase, and also So in the nitrate, nitrite reductases, and iron also used for the electron transfer in the photosynthesis. So it is a very important element. And the right side figure shows elements required for phytoplankton growth. And the horizontal axis shows the cellular ratio of elements normalized to carbon. So this is phytoplankton demand. And the vertical axis shows. Vertical axis shows mean dissolved concentration ratio to the also normalized to the carbon. Focusing on iron, there is a very low dissolved concentration in the seawater despite relatively high demand for phytoplankton, indicating that iron is a very variable element in the marine environment and easily deficient in the ocean. And this figure shows nitrate concentration by background, and circles represent a limiting element. Center color represents a primary limiting element, and outside color represents a secondary limiting element. We can see red colored circles indicating iron limitation, mainly in the Southern Ocean, also in the Eastern Equatorial Pacific, and the subarctic oceans. It is known that roughly 1/3 of the global ocean is limited by the iron deficiency. So understanding iron cycle is very important to understand the carbon cycle. It has been predicted since 1980s that iron plays an important role in marine biogeochemical cycles. However, the observed data were very limited owing to the analytical difficulties. The left figure shows an example. The observed nitrate concentrations are abundant even in 1990s, but those for dissolved iron are very sparse, and limited availability of observed data hindered our proper understanding of iron cycle. Right side figure shows the dissolved iron concentration, vertical profile of dissolved iron concentration, compared on 1997. And at that time, it is believed that iron is mainly supplied from aeolian dust, and the distribution is considered to be controlled by balance between these processes, mainly the one-dimensional local processes. So the classical view of marine iron cycle is one-dimensional or local processes, but later the international observational program called GeoTraces has been launched to accumulate precise observed trace metal data. And the characteristic distribution observed in several cross-sections obtained by GeoTraces have revolutionized our understanding of iron cycle in the ocean. Today, I'd like to explain some examples in the Equatorial Pacific and the North Pacific and the Bermuda Atlantic side. This is a study by Rising et al. They measured a lot of dissolved iron concentration in the Equatorial Pacific off of Peru, crossing the East Pacific Rise, and they found very high iron concentration near the hydrothermal vent, and the concentration goes downstream in the deep Pacific Ocean. And they plotted this dissolved iron concentration against hydrothermal helium, and they found that nearly linear relationship between dissolved iron and hydrothermal helium, indicating that iron behaves nearly conservative way. So the decrease in dissolved iron concentration in the plume is mainly controlled by dilution with the surrounding seawater. This is very surprising because we believe that iron supplied from hydrothermal vent is easily precipitated owing to very low solubility of iron in seawater. And subsequent more detailed analysis revealed that iron is not transported in the same way as the helium, but it moves downwards relative to helium. And they indicated that this descent involves reversible exchange of ion to the sinking particles. Another example I'd like to talk is the sedimentary ion transport in the North Pacific. Nishioka et al. Collected a lot of dissolved data in the North Pacific, and they found that significantly high ion concentration in the northwestern region, and especially in the intermediate layer. And they indicated that iron is originally coming from seafloor sediment from the Okhotsk Sea. This is the marginal sea. And they also indicated that intermediate water formation process in this area, peculiar in this area, are contributing to ion transport from this marginal sea to the open ocean. Subsequent modeling study confirmed their argument, and they also pointed out that processes by which ion moves back and forth between dissolved and particulate phase mediated by colloid significantly contributing to this long-range transport of ion. Another study is Taliabu et al. They measured simultaneously dissolved and particulate ion concentration in the Bermuda Atlantic site, and they classified particulate ion to the lithogenic and biogenic particulate ion. And they evaluated oceanic particulate ion by subtracting these two from the total. And they found that oceanic particulate ion is a major portion of the total particulate ion. And they also pointed out that generation of this oceanic particulate ion efficiently remove ion from the seawater. And this process is mediated by colloid, so they call this process as colloidal shunt. And they incorporated this process into their model and successfully reproduced the seasonal variability of dissolved and particulate ion concentration in the Bermuda Atlantic site. That was very difficult in the previous model. And they, taking advantage of numerical model, they extrapolated importance of this process into the global, and they found that this process is very important in the global scale, orange-colored area. So the accumulation of high-quality dissolved ion data, especially obtained by geotraces, have overturned the traditional understanding of ion cycle. Now we know that a lot of external sources are contributing to ion distribution and also inventory. And now we know that lateral transport and ion speciation is very important to determine the distribution. Although numerical models have been improved with the better understanding of ion cycle, the relationship between phytoplankton metabolism and ion cycle is still rudimentally represented. For example, in IPCC models, when evaluate the bioavailability of ion, the model usually uses bulk dissolved ion. There is no classification between these fractions. And also, the ion speciation is very sensitive to the oxygen levels and seawater pH, so the climate change must affect the ion speciation, so that's the primary productivity. But the current IPCC models ignore this route to change the primary productivity. So here are some expectations for the biogeoscapes. The IPCC models relate bulk dissolved ion to metabolism in phytoplankton because there was little information. If omics information provides detailed insight into ion utilization, it can improve the models. So even in the current ocean, there are areas where the degree of iron limitation varies seasonally. For example, the subarctic North Pacific is expected to be less iron limited in the winter and more strongly in summer. By analyzing such temporal changes, we may be able to elucidate survival strategy of phytoplankton in different iron levels and obtain implications for the response to the climate change. The combination of culture experiment and omics information may provide existing models with stronger constraint on various physiological parameters that are very difficult to obtain the traditional ocean observations. Thank you. Thank you very much.
Thanks. Impeccably timed. Any questions?
Thank you for an excellent talk and very interesting conclusions at the end. I was intrigued by this comment of how we can use omics to get a better insight into iron utilization. And do you have ideas of how that could work or examples of how that might work?
I'm a beginner for the bioinformatics, so I have no idea now. And I need to study in this meeting. Sorry.
Thanks for that great talk. I thought maybe Mac was going to ask this question, but I think I was just wondering if you've had any thoughts about processes besides primary production and nitrogen fixation that could be potentially iron limited, and thinking about maybe there's regions of the mesopelagic that might also be iron limited. That's okay.
No, I have no idea. But sorry.
My question is kind of philosophical because, I'm Noelle over here from University of Southern California. Do you want, do you feel like you want, to me, you seem like you're a chemist, and you're saying you want to integrate the omics information, and Mac asked how you want to do it. Do you feel like you want to learn the omics, or would you want to work with someone who knows the omics? How should we do this? Should we really share the skills, or is it?
Yeah.
What? How do you want to do it?
So I'm here.
Yeah.
Yeah. That's a reason to come here.
Okay.
So yeah, I need to learn some the.
Or do you feel like it's also, or would you rather just find an omics friend? I don't know. How do you want to do it? I think it's a question for all of us, and
yeah. Yeah.
It's all options, right?
Yeah.
Okay.
All right, so on that friendly note, let's thank Kazu and Scott as well.